The Ard. The Ard is a non-inversion plow built from a sharpened wooden beam drawn through the earth by a pair of oxen, fracturing the top few centimeters of soil and creating a shallow furrow for seed broadcasting. Because it leaves undisturbed soil between passes, farmers using the Ard cross plow their fields in two perpendicular directions, a technique that produces the squarish Celtic field patterns still visible as crop marks in satellite imagery. Plowed fields dated to around 2800 BCE have been confirmed at Kalibangan in India, and terracotta models of the implement have been recovered from the Indus Valley. The Ard cannot break heavy, wet clay soils, a limitation that determined the course of Northern European agricultural development. It remains in daily use in parts of rural Asia and Africa, repairable by any local blacksmith using available wood. Its shallow action does not invert the soil profile or expose subsurface material, which preserves the microbial structure of the topsoil in a way that inversion tools do not. The moldboard plow. The moldboard plow uses three components working in sequence. A vertical coulter slices the ground, a horizontal share cuts the base of the furrow, and a curved moldboard lifts the entire soil slice, twists it through 135 degrees, and lays it face down against the previous pass. A two-bottom configuration requires a tractor producing between 35 and 50 horsepower and operates at depths of 20 to 30 centimeters, leaving less than 15% of crop residue on the surface. The iron moldboard design uses mathematical curves on the moldboard surface to reduce draft resistance. Farmers in the 1700s refused to adopt iron moldboards, convinced the metal poisoned the ground. The moldboard makes heavy clay soils farmable by inverting the full soil profile, burying surface weeds and residue completely, and producing a clean, aerated seedbed. That same inversion exposes subsoil to wind and rain at a rate that generates measurable surface erosion on bare fields. The John Deere steel plow. The John Deere steel plow was constructed from a broken sawmill blade and is built to function in the heavy black prairie soils of the American plains. Cast iron is a porous material, and in damp, sticky clay, soil fills its microscopic surface pores and creates suction that clogs the blade. High-carbon steel can be polished to a density that breaks that suction, allowing the soil to scour the blade clean as it moves. Deere produced 2,000 units per year in 9 different sizes. Analysis of the Smithsonian's 1838 specimen reveals the moldboard was wrought iron rather than steel, meaning the self-cleaning effect came from the steel share and its polished finish, with the steel branding functioning as much as marketing as metallurgy. The plow is designed to remain free of soil adhesion in conditions that cause cast iron implements to clog and stall, making it functional in clay soils that standard European implements cannot work at all. The steam balance plow. The steam balance plow is a field cultivation system that addresses a mechanical constraint. An engine powerful enough to plow at scale is also heavy enough to compact the seedbed into an unusable state if driven across it. The Fowler system uses 2 traction engines weighing between 12 and 20 tons each, positioned on opposite headlands. Steel rope, up to 730 meters long, connects each engine to a central implement. One engine winches the plow across the field, while the other unspools. The balance plow frame carries right-hand shares on one end and left-hand shares on the other. At the end of each pass, the operator tips the frame, dropping the opposite set of shares for the return journey. A steam set covers between 2 and 4 hectares per day depending on implement width, while the engines remain on the headland and never contact the seedbed. The British government commissioned more than 140 sets of these engines to increase domestic food output during the naval blockade of World War I. The system keeps all engine weight off the field surface by transferring draft force through a cable, rather than through direct traction on the soil. The chisel plow. The chisel plow uses narrow pointed tines that penetrate to depths of 20 to 30 centimeters, breaking compacted layers through shear force while leaving 35 to 65% of surface stubble and root material in place. A 13-shank configuration requires more than 300 horsepower in heavy clay at depths beyond 50 centimeters, with each shank requiring approximately 20 to 25 horsepower for safe operation. The compacted layer the chisel addresses, called hardpan, forms just below the depth of standard plowing and acts as a barrier to root penetration and water drainage. Emergency chisel cultivation was used during the 1930s Dust Bowl as a response to surface exposure caused by aggressive moldboard farming across the American plains. The surface stubble left by the chisel acts as a windbreak and moisture barrier, reducing the rate at which exposed soil loses water to evaporation. The chisel plow is used in dryland farming regions and in minimum till and no-till transition systems where preserving surface residue is a management requirement. The disc plow. The disc plow uses rotation, rather than static dragging, to move through the soil. Concave steel discs, ranging from 260 to 810 millimeters in diameter, are mounted at a tilt angle of 15 to 25 degrees relative to the direction of travel, allowing them to slice and rotate as they advance. That rotation allows the disc to climb over rocks and tree roots rather than catch on them, making it suitable for stony ground, dense crop residue, and abrasive black cotton soils in India and sub-Saharan Africa, where a conventional share would sustain damage within a single working day. High-speed disc variants operate at up to 22 kilometers per hour. In March 2002, a Massey Ferguson 8280 using disc plows covered 620 acres in 24 hours in France, averaging nearly 23 acres per hour. The disc plow is used on soil conditions that static blade implements cannot work, and it reduces blade wear in abrasive environments by replacing sliding contact with rolling contact. The ridge plow. The ridge plow shapes the field surface into raised beds and drainage channels. Medieval ridge and furrow systems produced ridges between 5 and 22 yards wide and up to 60 centimeters tall, accumulated because non-reversible plows could only turn soil to the right, gathering material toward the center of the strip with each pass. Many of these ridges carry a characteristic S-curve, which is a mechanical record of the turning radius of an 8-oxen team, with the plowman beginning the turn early to keep the implement aligned on the headland. Those shapes remain visible in satellite imagery of English fields, preserved as earthworks in uncultivated land. Modern ridge-till systems create elevated beds 66 to 76 centimeters apart, maintaining 65% surface residue coverage while improving drainage on flat, poorly drained soils. The raised geometry produces a thermal effect. The ridge surface warms and dries faster in spring than flat ground, giving seeds planted at the ridge peak a soil temperature advantage that advances germination and crop establishment. The yeoman's keyline plow. The yeoman's keyline plow uses narrow, low-disturbance tines to cultivate the soil in lines that run slightly off the natural contour of the land. A standard subsoiler of equivalent depth requires more than 50 horsepower per shank. The yeoman's design achieves comparable penetration with less draft resistance, making it operable by smaller tractors on rough terrain. The slightly off-contour cultivation line redirects water moving across the field away from wet valley floors where it causes gully erosion and toward dry ridgelines where it infiltrates the soil. Field trials have recorded water infiltration rate increases of up to 300% on treated land, with 25% crop yield gains reported on degraded soil in Year 1 assessments. The implement is used in regenerative and permaculture agriculture systems, and has been adopted in German agroforestry programs as a tool for managing soil water retention under variable rainfall conditions. P.A. Yeomans developed it on his properties in Australia following severe drought and erosion, applying the principle that soil water distribution can be managed through the geometry of cultivation lines rather than through drainage infrastructure. The paraplow. The paraplow fractures the soil subsurface while leaving the surface undisturbed. Its defining component is an L-shaped leg set at a 45-degree angle, drawn through the soil at depths of up to 40 centimeters. As the leg moves forward, it creates a temporary void beneath the soil profile, lifting the surface by several centimeters and allowing it to drop back as the leg passes. The result is a network of vertical and horizontal fractures through compacted hardpan below, achieved without mixing infertile subsoil upward into the nutrient-rich surface layer and without disturbing the surface residue. The standard configuration requires between 30 and 50 horsepower per shank, and the field surface after a pass shows near zero visible disturbance. It addresses compaction in zero-till farming systems, where harvesting machinery progressively compresses the subsurface over successive seasons until water and root penetration are reduced. Researchers at the University of Campinas in Brazil have developed a rotary variant that pairs the slanted leg with a vertical milling cutter, reducing the power requirement and adapting the design for the conditions of tropical sugarcane cultivation. The Cockshut 66 bottom. The Cockshut 66 bottom consists of 66 14-inch moldboard bottoms assembled from 6 antique Cockshut plows combined into a single frame by volunteers at the Manitoba Agricultural Museum, engineered by Aaron Leaflore. The implement spans 23.5 meters and was pulled across heavy Manitoba clay by 5 roomly 3060 oil pull traction engines to set a Guinness World Record. A custom heavy-duty drawbar was designed to synchronize draft power from 5 separate century-old tractors while allowing the 23.5-meter implement to complete a headland turn. Rain before the attempt produced dense, sticky clay so resistant that a fifth engine was required beyond the original 4-tractor configuration. At operating width, the plow covered nearly 1.2 hectares in a single crossing of the field. Bill Cockshut, the former CEO of the Cockshut Company, was present and placed the first bottom into the soil at the start of the run. The implement demonstrates that the cutting and turning action of the plow scales in proportion to available power, but reaches a point where managing the machine requires coordination across multiple independent power sources and a purpose-built coupling system.